Now I am going to explain. Let me record first. Past. Okay. Now I am going to explain Norton's theorem. In this Norton's theorem, what actually states. So already we did with the Thevenin's theorem. The Thevenin's theorem extension. That means when you convert, when you transform that source, you are going to get the Norton's theorem. Okay. Before that, let us see the statement here. The statement is just similar to that of Thevenin's theorem. Only thing is there we have voltage source. Here we are having current source. There we have series circuit. In this we are going to have parallel circuit. Okay. So same thing, linear bilateral network. Linear means already we know what is linear, which obeying Ohm's law like that. As voltage increases, current should increase. Bilateral means it should allow both the directions. Current should, okay. Whereas diode, it is not going to allow in the both directions. Two terminal network. Simply the complex circuit is there. That complex circuit is replaced by current source in parallel with the equivalent resistance. So this is the actual network I'm having. This is the actual network I'm having. Let me take the cursor. Okay, this is the actual network, complex network, that is a huge network I'm having connected with one load. Now what I am going to do is I'm going to replace this actual circuit. I'm going to replace this huge circuit into simple Norton's theorem. Okay, Norton's equivalent circuit. That means whatever the huge network is there, just I'm going to replace it by one current source in parallel with Norton's resistance, and we connect that load to it. So this is the final circuit we are going to get. That means that actual circuit will be modified to this Norton's equivalent circuit. IN is parallel with RN. That means this load, whatever the load is there, that load we need to connect to this Norton's equivalent circuit. So we need to find the response. What is the response we are going to find? We are going to find the current through this load branch. So by using this current division, we get the value. Now after simplifying this complex circuit into Norton circuit, I can get the value of current IL by using current division. What is current division? IL is equal to total current into total current is IN, that is short circuit current, and opposite resistor for current source. It is opposite resistor by opposite resistor plus that load resistor. So this is the formula we need to write for finding the current through IL. Okay. So this is the thing. Let us take one example for solving this one. So how you will get this means, here whatever the network is there, suppose if load is there, that load is there now, that load we have to remove temporarily. Step one, we have to remove this load temporarily. After removing the load, we need to short circuit that path. After short circuiting, what you are going to get? You are going to have some current. No, let me go with the next page. This already we discussed. These are the steps. Those steps I'm going to give you. Steps are removing RL temporarily and short circuiting the terminals, so that we are going to get the current IN. After that, we will find Norton's equivalent resistance, same like Thevenin's resistance, and connect RL to the Norton's equivalent circuit. This RL is connected to this circuit, and finding the response, that is IL. Let us take one example here. The example I have already taken for the Thevenin's theorem, superposition theorem, nodal analysis. You can go through with my previous lectures. Okay. Again, I'm taking the same circuit for this one for the example purpose, because in order to verify the same answer. So let us take the 160 ohms branch. For this 160 ohms branch, I want to find the current through using Norton's theorem. Okay. What is the step one? Step one is removing the RL that I have removed here in the step one, removing the RL. And after removing this RL, what I am doing? I am going to short circuit the terminal. So I made this resistance is replaced by short circuit. You can observe in the step two. Okay, step one and step two. RL is removed and short circuiting the terminals to find what? Norton's current, which is nothing but short circuit current. So this short circuit current, how you will find? By making use of simple loop analysis. I will show you the loop analysis technique with the next slide. Let me Go with next page. Let me clear all first. Okay, this mesh analysis you can see here. This is the circuit actually I'm having. In this circuit, I am going to apply KVL. Okay, I'm going to apply KVL so that here I'm going to apply KVL. I'm taking the two loops. Two loops are there means two loop currents are there. That is I1 and I2. So one current is in all. Though both the currents I have assumed as the clockwise direction, so that through this short circuit branch, two currents are entering. That is I1 is entering in this direction, whereas I2 is entering in opposite direction. So what will be the short circuit current? So it is a difference only, no? That is Norton's current or short circuit current is I1 minus I2. So before that, we will find the I1 value by applying loop analysis. That is mesh KVL. Apply KVL. This is when you apply current is flowing like this means this will be the drop plus and minus. So minus 20I, that is V is equal to IR, no? If no voltage is there, just replace it by I into R. I is I1, R is 20. And here when we see this loop, current is entering from negative to positive. Negative to positive means positive. 100 is equal to 0. From this, I am going to get the value of current. Similarly, I can apply loop 2. In loop 2, what I am doing, the same analysis, plus is minus, because current is entering in clockwise means this will be the drop. Minus 20 I2, it is entering from positive to negative means minus it is, because previously negative to positive, but here it is positive to negative means it is minus 70 is equal to 0. From this, I am going to get the current as minus 3.5 amperes. Then actually, what is the Norton's current? We got no I1 minus I2. So just substitute the short circuit current is nothing but Norton's current, which is equal to I1 minus I2. I1 we got as 5 amperes and I2 we got as minus 3.5. Minus and minus we will get as 3.5. Okay, plus. Okay, 5 plus 3.5 is 8.5 amperes. Okay, let me go with the next slide. So it is 3.5. Okay, 5 plus 3.5 is 8.5 amperes. So we can connect that 8.5 amperes to the circuit so that we can find the answer easily. So after getting that, that is the Norton's current. Now let us find the Norton's equivalent resistance. All voltage sources are replaced by short circuit. Here 100 volts, here 70 volts is replaced by short circuit. When you made short circuit, this circuit will be looking like this. Whether it is series or parallel, let me check first. So this is approximately, these arms are there, no? I can stretch it out. So I am stretching out these arms and I am dragging this arm downwards. When I drag this resistance will come over here and this resistance will come over here. So when you apply some voltage source to it, how it looks like these two are in parallel. So if they are in parallel, you just do the product by sum, that is 20 into 20 by 20 plus 20, which is the Norton's resistance or equivalent resistance. The value is 10 ohms. Now what I am doing is I am going to connect this. I am going to connect this RL to this Norton's equivalent circuit. So what is the Norton's equivalent circuit? Current source in parallel with equivalent resistance. Current source direction is this one. This is Norton's current and RN value. We got these two values, no? Initially, temporarily we have removed one RL, no? That RL we need to connect now. Okay, that RL we need to connect now. This will be the circuit, new circuit. So RL is 160, RN is 10. You can see here RL is 160, RN is 10, and IN is 8.5. So just I want what current through 160 ohms, that is load current only, no? That is IL is equal to just applying the current division method. Just you apply this current division method formula, you are going to get the value of current through this branch. You can get by using nodal analysis also. So by directly using this formula, the steps will be minimized. That's why current division method I am doing here. So Norton's current is 8.5 and resistance RN is 10 ohms we got, and this value is RN is 10 plus 160, which is 8.5 into 10 is 85 and the denominator is 170. 85 ones are 85 twos are 1 by 2 value is 0.5 amperes. So this is the current. So for the Thevenin's also we got the same answer. For Norton's also we got the same answer. So any method we can implement for finding the response through particular resistor. Okay. Thank you for watching. Please subscribe and share. Thank you.